Hello everybody. I'm standing here right in front of you. I know that, quite sure about that fact. When I look down I see two legs and two arms, a torso, a bit of a belly, and I know that this is me. This is my physical self. I'm not sitting out there in the audience, and you guys, your bodies are your own. But how does the brain actually create this experience of a physical self in space? That is what I'm going to be talking about today. And there are three classical arguments that I will show you. The two first are old arguments, and the third one is a new experiment we have done in our lab last spring. So the idea is that inside my brain here, my brain is generating this experience of myself here in space. How do we know that? Well, the classic argument in psychology are based on these two observations. Now, you can have a perfectly normal body, but after brain damage, you might no longer be able to identify your own limbs. Or you might actually have lost a limb, but you still feel that you experience that missing limb as part of yourself. So, in neurology, we know that patients suffering from stroke, often in the right hemisphere, frontal and parietal lobes, and a paralysis on the left side, they can display this remarkable inability to self-identify their limbs. The doctor in the emergency room can lift up their hand, show it to the patient as part of the clinical examination, ask the patient, "What is this?" The patient will say, "It's not my hand. It's your hand, doctor. My niece's doctor." Or sometimes, "Oh, someone else must have sneaked in here in my bed beside me." This tells us that if you have damage to the association cortex, this experience of your own body can be impaired. Although you have an absolutely normally fully functioning body and your brain receives input from your nerves in the body. The other example is phantom limbs. We know that after amputation, 99% of upper limb amputees, for example, experience their missing limb. They don't have a limb, but they still feel it, like an invisible hand or an invisible limb. And this shows us that in the brain, there is some sort of body inside the brain that is being constructed. The third example comes from our own lab. It's an illusion. So the participant sits here. He or she is just looking here at empty space. There's nothing there. It just feels quite silly. The real hand is hidden behind a screen here. So you don't see your real hand. You just sit there, stare in empty space. And your hand is being brushed behind the screen. Nothing happens, kind of silly. But in about 15, 20 seconds, in the majority of participants, you can see how their face changes. They start to stare, they start to look. What is happening? Well, they start to sense something quite surprising and remarkable. They start to sense touch here, where they see the paintbrush move in empty space. And they develop this eerie sensation that they have an invisible hand. An invisible hand right in front of their eyes that they know is not there, they can see it's not there, but they just feel it, like a ghost hand perhaps, being stroked by the brush. Now, this tells us a couple of things. First of all, it shows how remarkably plastic and dynamic the brain's representation of ourself is. 20 seconds of a little bit of very simple stimulation like this can completely change your experience of yourself. Suddenly, empty space is you. Secondly, there seems to be something very important about the touch stimulation and the visual stimulation here. Something here makes the brain decide, hey, I don't have a visible hand anymore, I have an invisible hand, and it's located right here. And for cognitive neuroscientists and psychologists, we are interested in illusions like this because of what they tell us about how the mind works and how the brain works. So how do we measure this? We can try it ourselves, it feels kind of cool. How do we measure it? Well, there are many different ways that we have developed. This is one example. You can threaten the invisible hand and see if people are telling the truth by putting a sharp object right where the person said he or she had an invisible hand. And if you experience a strong illusion, you will flinch and show an emotional defense reaction. And we can measure how afraid you are by putting small electrode on the skin and we can measure your psychological sweat reaction, how much you start to sweat. The more you sweat, the stronger you feel the illusion. Another test we can use is to, after the illusion, ask people to close their eyes and use their other hand to point to where they feel their hand to be located. After the illusion, people point towards the invisible hand rather than to the real hand. And the greater than is pointing, the stronger they also experience the illusion. Or, and this is the great thing by working with humans rather than mice and rats, we can ask people what they feel, what they experience. So we can give them rating scales, visual analog rating scales, where they can report how strongly they felt touch on the brush, how strongly they felt an invisible hand, and so on and so forth. So we have done lots of experiments to try to figure out exactly what are the rules that determine when you feel this illusion. Is it just fantasy or imagination? People are being slightly metaphoric? No, we don't think so, because there are very precise rules that determine this illusion. First of all, what you see and what you feel has to happen at the same time. Timing is everything. You have to stroke empty space and the hand synchronously. You have to apply the strokes in the same direction. If you stroke in different directions, the illusion doesn't work. Nothing happens, even if you do it synchronously. It has to be empty space here. If you take an object that doesn't look like a hand, like a block of wood, put it in empty space, the illusion doesn't work, even if you stroke synchronously. And the illusion only works if you're close to the body. If you try to induce an invisible hand far away, it doesn't work. So, synchronicity, spatial match, empty space, and near the body. These are important information to us. It tells us something about where in the brain would we start to look for mechanisms that produce this invisible hand illusion. And this is important because it tells us something about how we experience our normal body in everyday situations. So we can put people in the brain scanner. This is called functional magnetic resonance imaging. It has revolutionized psychology. We can actually go into the brain and see what's going on. So we take healthy individuals awake. They can be doing tasks, or here they can perceive an illusion. We can completely measure how strongly they feel the illusion. This is the participant. This is the scientist outside. It's a big tunnel you go into that makes a lot of noise. And we can make images of the brain every 4 seconds. And we can scan every region of the brain at the same time. And our resolution are 3 by 3 by 3 millimeter voxels. That's great. We can get all the areas at the same time. And these regions light up when you experience the invisible hand illusion. These are areas in the parietal lobe, the posterior parietal cortex, and in the frontal lobe in the premotor cortex. This is part of the so-called association cortex. These are higher areas that integrate information from the different sensory modalities. So we're not talking about the early visual areas where information from the eye first reaches the brain, or the primary somatosensory cortex where touch signals are first processed. No, it's a higher order area where these signals are integrated. Now, if we take these two considerations together, the spatial and temporal rules of the illusion, the fact that we see activity in the association cortex, in these sets of regions, in the posterior parietal cortex and the frontal lobe, especially the areas in something called the interparietal sulcus and the premotor cortex. To us, this is important. Why? These regions receive anatomical connections from all the early sensory areas of the brain. And if you put in an electrode here, in a monkey, for example, you can find single neurons that respond when you touch the monkey's body, when the monkey sees an object approaching the body, or if you move body parts. It's illustrated here. So these areas contain cells that has the capacity to integrate all those senses. And they do so, these neurons fire if you touch the monkey and the monkey sees an object moving at the same place at the same time. They also don't fire if the monkey sees objects far away from the body. So these neurons seem to obey the same rules that we find determines the illusion. So we think maybe the two are linked together. Our brain imaging data suggests that. All right, but this is an illusion, fancy illusion. Can we be really sure this applies to our everyday experience of our own body? So next, we tried something we can call a disowning hand trick. The idea is that the person should look at their own hand, clearly recognize it, this is my hand, and then feel that this is not my hand anymore. It doesn't feel like me. Completely reverse of the invisible hand illusion, you could say. How do we do that? So the test person is now lying in the scanner. In this case, the male subject is looking at his own hand. This is his actual hand. And we simply stroke it with this little stimulation like this. It's very, very simple. The world's most simple experiment. You're looking at your own hand being stroked. Nothing could be more straightforward. But now comes the point. We will introduce mismatches between what you feel and what you see. So it should be so that when you see the hand touched, you don't feel anything. And then you feel something, but you don't see anything here on the hand. These mismatches between what you see and what you feel should, according to our theory, break down the feeling of ownership of that hand. Just like we can evoke illusory ownership of empty space, we should break down the ownership of the real hand according to the same principles. To do that, how do we introduce these delays? We have to use a little bit of technology. So you look at your hand through a set of head-mounted displays that we put in front of your eyes, right eye and left eye, that are connected to video cameras that film your own hand from the right perspective and present a high-quality 3D video feed to the goggles. So whenever there's no delays, you just get this experience, this see-through effect that you see your hand directly. Then we can introduce delays. So when you see the hand stroked, you don't feel the stroke because it's like a 500 millisecond delay. So then we can introduce the mismatch. And when we introduce this mismatch, we find that when people disown their hand, there is reductions in activity in very much the same areas that I just showed you. In the association cortex in the frontal lobe, in the so-called premotor cortex, in the association cortex of the parietal lobe, in the interparietal sulcus. They're very much the same regions as in the invisible hand illusion. And the stronger the suppression of activity in these regions, the stronger people say, no, it's not my hand anymore, when the visual and tactile stimulation is out of sync. So we think that these areas in the association cortex are continuously comparing and integrating visual, tactile, and signals from muscles and joints to maintain this internal representation of your own limbs in space. Now, how far can we go? Can we not just change the experience of a single limb, but maybe change your feeling of your entire body? Maybe make you feel that you leave your body and have some sort of out-of-body experience, or that you suddenly experience another person's body as your own. How far can we take these rules and principles I just talked about for the hand? So now we're going to try to apply them to the full body. But when we are facing the problem of the full body, there's a couple of new problems we have to think about. The first point is quite obvious. As I stand here in front of you, I see you from this first-person point of view, right? Because my eyes are fixed here on my skull. I can't move my eyes around. They're always fixed here. So this is how we see the world. And a lot of thinkers before me have emphasized this. That there must be something special about the first-person point of view and the sense of your own body. This is an old drawing from Gibson, the famous American psychologist, as he lay in the sofa and he observed his legs and his hand with a little cigarette there from a first-person point of view. So what we want to do is we want to take someone's eyes and move them around in the lab, but having an optical nerve intact. Like now, if a thought experiment, if I can take my eyes and move them out there, so I sit next to you, and I turn around, I see myself from that perspective. Optical nerve is still intact, connected to my brain. Would my consciousness now move over and sit there with where my eyes are located, or will it still be here in my body? So how important are the first-person point of view for the experience of your full body? So this is how we did the experiments. Obviously, we can't move people's eyes around, but we can move the cameras around, which are connected to the head-mounted displays, sending the video signals in real time. So you see yourself from the back, 2 meters from the back, and you should sit still. You should not move that this reporter is doing because they get excited. You should just sit still. And then comes the synchronized visual and tactile stimulation that is so important. So I move my hand towards the point below the cameras here. And every time I move my hand to this point below the cameras, I touch his chest here, which he can't see. Now, the brain's now trying to put everything together. The new perspective, this object moving towards the cameras touches, and bam, it reinterprets reality. And now you experience that you're sitting here in a different place of the testing room, that I'm standing in front of you, not behind you, and that I am touching your chest directly here with my left hand here. And what about this guy? The guy who still sits in the middle of the testing room. You know it's you. You remember that you walked in and sat down there when the experiment started. But it doesn't feel like you anymore. It's like the disowning hand trick. Now you disown the whole body. It's not me anymore. Maybe it's a mannequin, someone said. And this is how we test it. So we can threaten the illusory body. This is another guy from the BBC. And then we attacked his new illusory body. He reacts. And if we take naive participants, it doesn't do anything, and then we do that, and we measure how much they sweat, they are much more afraid when we do that after a period of synchronous touches compared to everything else is the same. You see the same threat, it looks as scary, but we have touched the two bodies out of sync, not eliciting the illusion. Then they are less afraid. So it's a perception illusion. It's not just like watching a scary movie. Now, we can also threaten the real body because you're safe now. There's no one home. You're sitting 2 meters behind. So when we move a knife close to your back of your neck here, slowly, it's all safe. No one is going to get hurt. Everyone knows that. But still, if you feel someone moves a knife behind you, it feels a little bit slightly uncomfortable. And in the control condition now, where we touched the two, we made the asynchronous stimulation, people are a little bit afraid because they feel that we move the knife behind them. But in the illusion condition, they're cool about it. They feel that they're sitting far away from the knife. This knife is now close to something like it's someone else, although they know it's themselves. What about body swapping? What will happen if you look down and look at a new body? Because in this experiment, you see the room, but you don't look down. So if you look down, we can present a new body. It can be any kind of human-like body. And as long as we do the synchronous stimulation of the two bodies at the same place at the same time, you experience, hey, this is me. So you get it here. We put the cameras up here on the head of the mannequin, looking down. You stand here, you look down, you wear the head-mounted displays. You see the mannequin from the first-person point of view. And then we stroke the mannequin here and your body at the same time at the same place. Bam! You feel suddenly that this body is you. It doesn't matter if you have clothes, the mannequin is naked, or you're a man, or the mannequin is a man or woman. It works equally well. And again, we worked out all the rules that determines this illusion, and they turn out to be very similar to the rules for the invisible hand illusion. So synchronicity is everything. You have to apply the visual and tactile stimulation at the same time. Same direction of the strokes. You have to have a humanoid-like body shape. If you put something that doesn't look like a human, like a table or a block of wood, the solution doesn't work. You have to look at this body from a first-person point of view. If everything else is the same, but you're looking now at the mannequin man standing far away, it doesn't work, even if you do everything, follow all the other rules. And you actually own the entire mannequin. It's not just where we stimulate. It's not some kind of belly illusion. You feel that all body parts are your own, not only the point we are stimulating. I will take some questions later, because I'm sure there are a lot of questions, but I have to stick to the 30-minute video recording. Right, so size doesn't matter. If the body is proportional and we follow all those rules, it actually doesn't matter if you're small or large. You can be experiencing how it is to be a Barbie-sized doll. So here's the little doll down here, and now we put the cameras here, first-person point of view. This is what you see if you're a participant lying here. You see this hand stroking your legs. The scientist is stroking your corresponding leg at the same time, matching everything. So everything you see and feel matches. Now, if you experience an illusion, this is quite surrealistic is the best word, because you're now living in a world of giants, and you see this massive hand coming in, and you can sense the weight of that hand. And these objects that you present feels enormous. And the stronger you feel this illusion, the smaller the body, the bigger the world. So size doesn't matter as long as we follow all the other rules. And this tells us also that the way you experience the body directly influences how you experience the world. So the way I perceive all of you guys now depend on my own body experience. But that's a different story. Now, we do imaging experiments again, of course, to understand more about the brain mechanisms, right? And we're interested in the multisensory areas of the brain, so we can induce these mannequin illusions in the scanner. A test person is lying here, looking at the head-mounted displays, and you can then present different objects, control objects, the mannequins from the first-person point of view that triggers the illusion. And then we do the stimulation. And the most important experiments here, the key experiments here, is to see how do you get that feeling of owning, of having an entire body. You know, I have 2 arms and 2 legs and this torso here, and they're all connected. It's not fragments of me. They're all connected into one unified whole. How can we get to that wholeness of the body? So these are the experiments we try to get at that. So we induce the illusion by stimulating different body parts. So we can induce the full body illusion by stimulating the hand, or by stimulating the belly, or by stimulating the foot. And we look for responses in the multisensory areas. This is just one example when we stimulate the belly. The very similar areas light up as with the invisible hand illusion. But the crucial thing is we see areas that are activated regardless if you induce the illusion by stimulating the hand or the belly or the foot in later experiments. So the yellow zone here is in the multisensory area where you induce the illusion by hand stimulation, red by belly, and this here is orange zone. It doesn't seem to care. And we think here there are neurons that integrate visual and tactile signals across multiple body segments. So here we think there are neurons that care what is happening to your hand when you look at the belly, or that integrate signals from your foot and your hand. We've done a lot of experiments to actually prove that with the highest possible resolution of imaging technology. So to wrap up here, just the principle of full body ownerships, first person point of view, humanoid body shape, but it might work with an invisible full body. We're examining that right now. There's integration of visual somatosensory signals, the same rules, same time, same place, near the body. And then we think the difference between experience of a single limb and a full, rich, coherent body experience is integration across body segments. Now, what else can you do? Well, you can do something like this. If you combine the full body illusion and the outer body illusion, and you can actually, during an outer body illusion, what happens if you turn around and you face your old body and you shake hand with your old body? Now, clearly that will break the illusion. It's a little bit too weird. So in these experiments, put cameras on the head of the scientist. The test person stands here. We induce this illusion by hand shaking. So they squeeze their hands in synchronous way like this. And then the perspective is consistent. So you look at yourself from the perspective of the scientist, and you get the full body illusion that the scientist's body is now your body. And then you shake hand with yourself. You can recognize, you know that you're looking at yourself, but you feel everything from the scientist's body. So even though you shake hand with yourself, all your sensations originates from your new hand, i.e. the scientist's hand. And it just shows you that these body illusions are perceptual illusions. You can't think them away. It's not just imagination or fantasy. It doesn't matter if you know about the experiments, they work equally well. So we think about these body illusions more similar to the kind of optical illusion that you can see in museums. You go into the museum, they show these fascinating optical illusions. You know they're illusions, but you still see them. And we think these body illusions works the same way. So what is this good for? Are there any applications? Or is this experimental philosophy where we get new information about consciousness? But can we use it for something? Well, I'm very excited because right now there is a lot of interest in engineering and computer science and robotics, how we can extend the body, help paralyzed people or people who have lost a limb by giving them new advanced robotic limb devices, or give normal individuals almost superhuman strength and skill by variable robotics. These are just examples from different labs in the Europe and US. We are not involved in these specific experiments, but I'm showing you that there are a lot of people interested in this idea that you can extend the body. And this is, for example, how a paralyzed people or monkeys can control advanced prosthetic limbs, or a paralyzed person could walk wearing a robotic exoskeleton. Now, at what point does this technology stop being just a tool and become fully fused with your own body representation? When does this tool start to feel exactly like real limbs? And is that a good thing? Could it be helpful for the user to feel a robotic hand exactly as your own hand? Maybe it is. Maybe you can react faster, use it more intuitively. Maybe you don't have to train so much. So we are quite interested in that. And I will show you one example, if I have time, on an application. Now, other area of applications are in health. there are many disorders where one can think that maybe the body experience and the way the brain creates this model of your body as distinct from the world is somehow disturbed or starts to be loosened up. For example, in schizophrenia or in certain psychiatrical disorders involving dissociation, patients describe that this boundary between self and non-self, self and the world, starts to be loosened up. We don't know why. We don't know what exactly happens in schizophrenia, for example. But our findings could give some new ideas that we can start to do experiment along that direction. We also know that in, for example, eating disorders, patients often have disturbances in how they perceive their body and feel about their body. And it would be interesting to see if this kinds of experiments I showed you here could be used to learn more about these disturbances of body image in eating disorders. And of course also to in rehabilitation of stroke patients that might have these body neglect problems, that they don't really recognize their own limbs. And it could be helpful in physiotherapy to get going, to know more about their specific problems. One application that we have been working on together with colleagues in Lund, like Johan Lundborg and his team, who's a hand surgeon, and Fredrik Sibelius at the Lund Engineering School, is if you have an advanced robotic hand like that, can you make amputees experience this advanced robotic hand as your own hand, completely merged with your full body representation? I was a little bit skeptical because amputees, amputees don't have a hand anymore. So if you're going to make a prosthesis, there's a problem. Where do we stimulate? So with a fully limbed individual, if I'm going to elicit an illusion that a prosthetic hand is your own hand, I would have to stroke exactly here on the finger and exactly on the test person's real finger. If I stroke up on the arm, the illusion doesn't work because of this spatial incongruency. If you are an amputee, you have a residual limb or a stump, but you don't have a hand. But we can use their phantom. How do we use their phantom? This guy still experiences his hand. It's out there like an invisible hand. So we have to touch his phantom fingers and then stimulate the fingers of the prosthesis. So first we need to know where are the phantom fingers and how do we stimulate his phantom fingers? Well, it turns out that on the residual limb or the stump, there's different parts here where you can touch. And if you touch this part on the stump, the person will say that now I feel that you're touching not only my stump, but I feel it also out in the fingers of the phantom. So if you touch here, the patient will say, you touched me on the phantom thumb. Down here, no, it's the phantom index finger, and so on. Sometimes you can map out the whole hand. So in this experiment, I'm stroking the index finger of the prosthetic hand, and I'm stroking his phantom index finger at the same time. That congruency between what the person sees and feels kicks in the illusion, and suddenly the amputee would say, it's my hand, I can see my phantom. The prosthesis feels like my own. And it also works with more robotic-looking hands, as long as they have a humanoid body shape. And we have done a lot of experiments to actually prove that this experience is genuine in these amputees. So to wrap up, I only had half an hour. I've been talking about the problem of how we experience our own body in space as a distinct object from the rest of the world. I've tried to convince you that we can do experiments in the laboratory. It's not just philosophy anymore. I've tried to convince you that we think that there are certain areas in the association cortex that are crucially important to continuously compare signals from eyes, skin, muscles, and joints to create this internal model of your own body, both for limbs and for full bodies, where there is an additional integration of signal across different body segments. And finally, I talked a little bit about applications and how we can project or extend this experience of your own body to incorporate external technological devices. So finally, I'll just like to thank a few of the people who did the experiments and work in my lab. This is our team. We sit over here at the Department of Neuroscience. And Giovanni Gentili, he did the disowning hand trick that he published earlier this year. Arvid Gutestam has done experiments on the out-of-body illusion that I showed you. Björn van der Hoort did the Barbie-doll illusion experiments. He's still a PhD student in the lab. And Valeria Petkova did work on the mannequin illusion, and she's now doing her clinical training in Germany. So thank you very much, and I'm happy to take questions.